So we added a plane and we added a box, a rectangular prism shape. But I think the next thing we wanted to do is make it so that we can move and rotate our camera so we can see our scene from different angles. So let's see if we can do that real quick. Make the ability to rotate the camera and move the camera around. If we look at our camera class, there it is. Yeah, we don't have, oh, we do have a translate. So we have the ability to move the camera. That's cool. But we can't, at this time, rotate it. So what we want to do is have a rotate camera. Or maybe what would be better is like a look at, where we could say, look at this point, and the camera would rotate itself towards that point. That would be cool. In order to do that, we need to be able to rotate a vector, or three-dimensional vector, around the X, Y, and Z axes. So we're going to have to do a little bit of vector math. But let's go to our vector 3 class, and let's add some rotation methods to this. Or a rotation method. I guess we could just do one rotate. So we're going to add a public, have it return the rotated vector, vector 3, rotate. And we want to know how far we're rotating around each of the axes, X, Y, and Z. So I guess we'll just put X, Y, and Z. Double Y, double Z. Okay. So we got to look up some formulas on rotating vectors, three-dimensional vectors. We're going to use some trigonometry for this. And it's probably more intuitive if we make these in degrees, although the sine and cosine functions in the Java math class use radians. So I guess we'll convert them. Assume that X, Y, and Z are given in degrees, and then we'll convert it to radians. So yeah, let's just start with, well, maybe we want to just leave them in radians, and then if we're calling the method, convert it. I don't know. What do you think? Should we have it use degrees or radians? You can see it either way. All right, we'll make it degrees. So then we'll convert these to radians. So x equals math dot 2 radians x, which again just divides by 180, multiplies by pi. Y equals math dot 2 radians y.
For the input of this, are we putting the degrees you want to rotate each, like, so the input is 3 doubles. Is that how much you want to rotate just the x direction by how much you want to rotate the y direction by?
Correct, yeah. So each of these x, y, and z represents the number of degrees around which you're rotating each axis. So rotate 45 degrees around the x-axis, 0 degrees around the y-axis, etc. Yeah. Okay. And now we want to calculate the new x, y, and z angles. And we sort of, I think it can have an effect depending on like what order you actually rotate around the axes. So I guess we'll just do it in X, Y, Z order. Makes sense. So we're going to first rotate, do the x-axis rotation, and then we'll do the y-axis rotation and the z-axis rotation. And so maybe it'd be better to split that into 3 different methods because it's gonna be less confusing that way. So let's do that. Let's just make a individual vector 3. Let's do a rotate x. Radians. We'll have this one take radians. This one can take degrees. So to rotate around just the x-axis, we're going to calculate the new x, y, and z components of the vector. So let's see, double new x is going to equal the old x multiplied by the cosine of the angle, radians, plus the z times the sine of the angle, radians.
So rotate x, does that mean we're rotating around the x-axis?
Yes. Yeah, this will rotate around the x-axis. Alright, that should be the new x component and the new... Oh, actually this is... I'm looking at the z-axis.
Yeah, because if we're rotating on the x-axis,
then yeah, the x shouldn't change, yeah. So this is actually the formula for rotating around the z. Double new y is going to be x times the sine, math dot sine of radians plus y times the cosine, math dot cosine radians. Let's see, this one I feel like should have been subtraction. Yes, this one should be minus. X cosine theta minus, I got this all mixed up. This would be y sine theta, and then the y is x sine theta plus y cosine theta. Okay, that looks right. And then the z doesn't change. So our vector 3, a rotated vector, is going to be new x and new y and the same z. Okay. So now we've got to do y and x. Let's see. Vector 3, rotate. Let's do y next. Double radians. Okay, so we gotta calculate a new, double new x. And if we're going around the y-axis, then the x is gonna be x times the cosine of the angle plus z times the sine, math dot sine radians. Okay, and the new y coordinate is the same, so we can just give it to a new z coordinate, and z is going to be negative x times math dot sine radians plus z times math dot cosine radians. Negative x sine theta plus z cosine theta. Okay. So return new vector 3, new x X, same Y, new Z. And finally, rotating around the X-axis. So we don't need a new X, but we do need a new Y, which is going to be Y times math.cosine radians minus Z times math.sine radians. And we need a new Z. So double new Z. And that's going to be Y times math.sine plus Z times math.cosine. Then we can return new vector 3, same X, new Y, new Z. Okay. And then for convenience, we have this method that will do all three and just call those other methods. So, well, yeah, no, we're missing a return statement. Okay. So, vector 3 rotated equals rotate X, X, I'll say this dot rotate X, just to clarify. And then we need to take that one and rotate it, rotated dot rotate Y by Y, and rotated equals rotated dot rotate Z, Z. And then return the rotated vector. Okay. That should work, I think. So now we can add a method to the camera class that allows us to rotate the camera. All right. So let's jump over to the camera here. Let's just add a simple rotate for now. So public void rotate. We need X, Y, and Z. This will be in degrees. And we'll say we have to rotate the direction vector and the up vector both by the same amount. So we can say direction equals direction dot rotate X, Y, Z. I already had it there. And up equals up dot rotate X, Y, Z. Simple enough. So now, when we're building our scene, let's see if we can rotate the camera down a little bit, maybe scoot the camera up. Save this. Alright, so I'm going to go to the Raymarching panel. I want to go to the generate scene. So we create the camera. Let's move the camera up. Camera dot translate. So we need to give it a displacement vector, u vector 3. Let's go to the right a little bit, so maybe 3 to the right, and let's move it up like, I don't know, 7 and 0 on the Z, and then let's rotate the camera. Rotate. Okay, so rotating around the x-axis should tilt it forward and back, so we want to rotate it downwards. I think that's going to be a negative rotation. I don't know. Let's try negative 30 degrees along the x. The y would yaw the camera left and right, so let's not rotate it that way at all. And then z would tilt it side to side, so let's not do that either, just for now. Okay. Let's see what happens when we do that. I see nothing but sky. Okay, maybe we looked up instead of down, so maybe it shouldn't be negative. Let's see. I might have got my direction backwards. Oh, Raymarching panel. So let's try 30 degrees. Positive. Hey, that's what we were going for. Yeah, okay. So I guess, yeah, the direction must be reversed. But yeah, we got that three-dimensional box. Very good. Now, right now, all of our shapes are stuck at the origin. We don't have any way to move the shapes around the scene. So why don't we create a translate SDF that allows us to move the shapes to different positions. So let's create a new class here. This is going to be regular Java class. Let's call it translate SDF. Finish. Okay, and this is going to extend regular SDF. And so it's going to take an SDF that already exists and just move it to a different position, so it's no longer stuck at the origin. So we need to store the original SDF. Let's just call it SDF. And then we need to know a vector for like where we're moving it to. So a displacement vector. Vector 3 displacement. We need a constructor. That takes in the other SDF and the translation vector, vector 3 displacement. And we store these. This dot SDF equals SDF. This dot displacement equals displacement. And then we need to override get distance and get material. Okay, and I'm pretty sure for getting the distance with the translated object, all we actually have to do is translate the point in the opposite direction, opposite of the displacement vector, and then get the distance. And then that will cause the object to move in the direction of displacement. So we could do something like point equals point dot subtract displacement, and then we can return SDF dot get distance. to write the get material. And we're just going to return the material of the SDF because that's not changing by translating it. Yeah. Although I guess technically we should translate the point first too. In case this material, like we don't have materials that change based on where they're translated, but we might could add that later. Have like a checkered material that is like a combination of two materials in a checkerboard pattern that actually would not be that hard to do. And you would want to translate the point for that. Okay, so let's see if this works now. If we can, let's maybe move the sphere to one side of the box or something. So if we go to our scene generation, here we created the sphere. Let's move the sphere, translate it using our new translate SDF by taking the original sphere and translating it by a new vector 3. And let's translate it to the right. I don't know, like it's radius, maybe just like 4 or something like that. 0 up and down and 0 forward and back. Actually, let's translate it back a little bit too, just to see. Okay, so now the box should be in the same spot in the center, but the sphere should be to the right and back further, if this is working correctly. Let's see. I think it did it. It is to the right further. Is it back a little bit too? Can't tell. I think so. It moved. So seems to be working. Awesome.
Could you go back to
Yes.
generate scene spot?
Yes. Generate scene. We're going to write a method in the material class that will take that material and blend it with another material with some kind of blend factor ratio from like on a sliding scale from one of the materials to the other one. And then we can use that for the regions where the two objects are being blended together to get a cool looking effect. So let's see if we can do that in the few minutes we have left. So we find our material class, and I think yeah, we can add this blend method at the end of our material class here, and it will return a new material that is the blended material. And we need to take as a parameter the second material that we're blending with. We'll call it other, and then we need to know how much of a blend to do, so we'll call that ratio. And what we need to do for this material is we need to blend the different values, right? So we have the color, and the best way to blend it is to blend the hue values and then blend the saturation, and then we'll blend the diffuse, basically just like it's like weighted average. And the only part that's sort of tricky is the hue, because of the way it is circular and wraps around, right? So we've got to find the best way to do that. So let's declare a variable for what the blended hue is going to be, and that hue is, it's going to depend on which one is larger. So it's sort of like when we did the distance between vertices on polygon is very similar thing. So there's probably lots of different ways to do it, but what makes sense in my head is to check to see if this hue, and actually rather than calling this hue over and over again, or get hue, so it might be slow. That's fine. It doesn't. It's just gonna happen once. So all right. Anyway, this this hue, if it's larger than the other hue, then want to see if the difference between this dot get hue minus we want the shortest distance between the two hues, basically. Other dot get hue. So if we subtract those, making sure to subtract the larger one first, and if that is smaller than other get hue plus 1 minus this dot get hue. So adding the 1 is like going the other direction around the circle to get to it. Oops. Let's see, will it fit if I do that? Nope, I gotta go further. Let's try this. Okay, so if it's shorter to go that way around the circle, then the new hue is going to equal this dot get hue minus this dot get hue minus the other dot get hue. And then we have to scale it by the ratio. So we're going to multiply that difference times the ratio. Yeah, so we're basically moving the hue towards the other hue by subtracting the difference, but scaling the amount we move towards the other hue by the ratio. Yeah. So that was in that case. Now if it was shorter to go the other way around the circle, then instead hue is going to be this get hue minus, not minus, plus, because we're going the other way this time. So we're going counterclockwise, I guess you would say. Other get hue plus 1 minus this dot get hue, and scale that by the ratio. Yeah, but this could result in the hue being larger than 1, and we want to scale it back down so it's not larger than 1. So if hue is greater than 1, then we'll just subtract 1 from it. Let's see, it's 1, because it should be a number from 0 to 1. Okay. So that was all if this hue was larger than the other one. Otherwise it's the other way around, and we need to reverse this stuff. Maybe there was a more efficient way to code this, but oh well. Other dot get hue minus this dot get hue is less than this dot get hue plus 1 minus other dot get hue. Okay. Check to see if which way around the circle to go. So if other dot get hue equal to this dot get hue plus other dot get hue minus this dot get hue times the ratio. Almost there. Else hue equals this dot get hue plus 1 minus this dot get hue plus 1 minus other dot get hue times ratio. And finally check to see if hue is greater than 1, then hue minus equals 1. And now we have a valid hue. That's kind of a mess. There's got to be a better way to do that, but this should work. Okay. So now we need to do the saturation. So that is just an average, a weighted average. That one shouldn't be difficult. So double saturation equals this dot get saturation plus, what's the method? Plus the difference between the two saturations. Let's see. So it would be other dot get saturation minus this dot get saturation, and multiply that times the ratio. So that's the new saturation. And then we need to do that with the diffuse as well. Diffuse equals this dot diffuse plus other dot diffuse minus this dot diffuse times ratio. Beautiful. Now we can create this new material that's the blend of the two. So first we have to create the color. So color equals color dot what is it? Get HSB color. And HSB is the hue that we calculated, the saturation that we calculated, and I don't know the brightness matters because we calculate the brightness when we're doing the lighting, so the brightness doesn't really matter. I'll just put it in 0.5. So there's the color, what? Oh, right, those are floats. Okay, fine. Cast to a float, cast to a float, and put an F to make that a float. Okay. Now finally we can return a new material with that color and diffuse that we calculated. Whew. Okay, hopefully this worth it because that was kind of messy. All right, we're going to create one more SDF class that's going to be this blending union, or smooth union we'll call it. So let's do a new file. Next, I'm going to call it smooth union SDF. And it's extends SDF, and we need two SDFs that we're blending together. B. And we need to know the ratio that we're blending, which with this algorithm they call it K, so I guess we'll call it K. And we need a constructor, public smooth union SDF, SDFA, SDFB, and double K, how much to blend them. So I believe if K is 0, then this should end up being equivalent to just a regular union, I think. So this dot A equals A, this dot B equals B, and this dot K equals K. Alright, now we're going to override our get distance. Vector 3 point. Okay, so we need to first get the distances to each of the two SDFs, and then we'll blend them together. So double distance to A is going to be A dot get distance to the point, and double distance to B equals B dot get distance to the point. Okay. And then we've got to calculate this number, this value H, is what they call it. And it is going to be 0.5 plus 0.5 times the difference between the distance to A and the distance to B divided by K. And then we need to make sure that H isn't negative. Like H has to be between 0 and 1. So we're going to say H equals math.min, math.max, H 0 and 1. So this should clamp H between 0 and 1. And now we're going to calculate this final distance, which we'll call M for some reason. And that's going to be the distance to A. This is the blending part, where you do the difference between the distance to B and the distance to A, and you multiply that by that H value that we calculated. And then the final value that we return is M minus K times H times 1.0 minus H. I'm not really sure why that formula does what it does, but it's cool looking, so we're gonna see if we can get it to work. Alright, now though we need to blend the two materials, so when we get the material, that material needs to be blended between the two. So let's override the get material, public double get material vector 3 point. Okay, so we kind of need to repeat some of the same calculations here, because this H value is going to be the ratio that we're blending the materials to. So we just need to redo these lines here to calculate H, and then we can use that H to blend the materials. So we're going to return A's material at that point, blended dot blend with B's material at that point, with a blending amount of H, or the ratio, the blending ratio of H. A get material at point dot blend, B get material at point H. Why are you not happy? Material. Oh, I said this is returning a double, and it's not. It's returning a material. There we go. Now we're happy. Okay. Assuming we did all that correctly, we should be able to now blend these two shapes together. So let's test it out really quick, and we'll be done for today. And I'm probably done for this project, and I'll just put up some other additional stuff for you guys to add to it, but pretty much done with the basics. So let's see here. Raymarching panel. We're generating our scene. Let's see, we've got a union between the sphere and the plane, and then we union the box. Let's change this up. I wanna smooth blend the box and the sphere. So let's do a smooth union SDF between the sphere and the box, and let's do a blending value of, I don't know, 0.4 maybe. And then we'll just union that smooth blend with the plane, so we get the plane in there as well. So that we should see the sphere morphing into the box, and the colors should transition between the two colors, if it works. Let's see. Cool. Yeah, it's working. And if we increase the value of that decimal, it will do more of a blend. Let's see. Try 0.7. Yeah, pretty cool. It's gradually shifting from one to the other. So, all right, that's enough for today.